Good afternoon. I welcome you to the session of experimental methods in fluid mechanics. Today we will discuss about pressure measurement using probes. How we can measure pressure using multi-hole probes, and we have discussed in my last few lectures the measurement of pressure using gauges, and we have seen that we can measure pressure using gauges, and that range of pressure which we can measure may be very small to very large, and for that we have discussed about the operational principle of different instruments. So, today we will discuss about another instrument which is used to measure pressure, and we will see today that this instrument, rather I mean these probes, multi-hole probes, are used in the area of fluid mechanics, in the area of experimental fluid mechanics to be precise, with some with having some advantageous features. So, we should know that if we use measurement probes, why these probes are important, rather why these probes are very common in measuring several flow parameters, that we will know. Multi-hole probes has become very common to determine different flow parameters like total pressure, static pressure, flow velocity, and most importantly the flow angles even in a 3-dimensional flow field. So, not only that, the probes, we have seen that we using gauges we can measure pressure, gauge pressure we can measure, but the use of probes allow us to measure simultaneous detection of total pressure, static pressure, flow angles, flow velocity. Now, and these mechanical probes are having a few advantageous features over other pressure measurement measurement instruments, like the simple in operation, then low cost, and also their maintenance is not very difficult. So, today we will see that we can use pressure using multi-hole probes, but we will restrict our discussion in using 3-hole and 4-hole probes. So, we will discuss multi-hole probes, and we will discuss about two different probes, that is 3-hole probes and 4-hole probes. So, as I said that these probes are important because using this instrument we can have simultaneous measurement of static pressure, dynamic pressure, flow velocity, as well as, which is very important in the area of experimental fluid mechanics, is that how we can measure flow angles. So, these parameters can be measured simultaneously using multi-hole probes. So, now as I said that we can measure static pressure, we can measure total pressure, then measuring this total pressure we can measure the flow velocity. We will see how we can. Now, before that, just we will try to recapitulate. We have learned from our undergraduate fluid mechanics course what is static pressure, what is total pressure, and now in continuation of that, today we would like to discuss about that what is static pressure probe, what is stagnation pressure probe. So, first I would like to discuss about static pressure probe. So, I will write the what is static pressure probe, and what are the name suggests that we can measure static pressure, and we will see that if we the probe is having facilities so that we can measure static pressure, stagnation pressure, flow velocities and flow angles. So, the static pressure, if you would like to measure static pressure using probe, then perhaps how we can measure, rather what will be the construction of the probe and the operational method, principle by how we can measure static pressure, that is what I would like to discuss now. If you would like to measure static pressure, say I am writing, then it will help you to understand the operational principle of the probes in a better way. So, this static pressure probes are sometimes used to obtain static pressure measurement. That is obvious. Where? That is obvious because the name itself suggests that we can measure only the static pressure. So, that static pressure probes are sometimes used to obtain static pressure measurement. Where? So, we can use this in the flow field rather than at the boundaries. At the boundaries. So, this is one aspect. So, if you would like to measure static pressure using probe, we cannot measure at the boundary, rather we can measure at the place which is far away from the boundary, that is in the flow field. Now, this static pressure probe largely in cylindrical shape, these probes are cylindrical tube, and these probes are placed, basically these probes are placed in parallel to the flow with static tappings located on its body. So, we have to place the probe, which is placing should be in parallel to the flow field, and the probe itself is having static tapping. A variety of configurations are available: wedge shape, conical, cylindrical, but the objective is that we should place the probe which is in parallel to the flow field, and we should have pressure tapping, otherwise we cannot measure static pressure. So, now question is, if we do not place the probe in parallel to the flow field, then what will happen? If we do not place the probe which is in parallel to the flow field, we won't get the correct results. Now, another important condition is that since we need to place, rather we should place the static pressure probe in parallel to the flow field, so we cannot use this probe in places where the velocity gradients are very large and turbulence is there. So, basically the static pressure probe is having restriction, that means this probe is not suitable for the places where flow field is highly chaotic and there exists a velocity gradient. So, this is not suitable. So, that means I can write this is restricted to the flow field where velocity gradient is not very high and turbulence is small. So, this is what is static pressure probe. Now, so we have seen that static pressure probe is used to measure static pressure, and important condition is that we need to place the probe in parallel to the flow field. The probe axis should be in parallel to the flow field, and since we cannot place in perpendicular to the flow field, then we can see, rather we can understand that the use of static pressure probe is restricted to the flow field where velocity gradient is not very high and turbulence is small. So, now we will see what is stagnation pressure probe. Now, second is stagnation pressure probe. So, this probe is used to measure stagnation pressure, the name suggests. Now, this is used to measure stagnation pressure. Another thing is that, see, since it is used to measure stagnation pressure, so again we have to place in a flow field where, that means the axis of the probe should be parallel to the flow field. And now question is, at the point where you would like to measure the stagnation pressure, the positioning of the probe will definitely disturb the flow field. There is no doubt about it. So, basically if you would like to measure stagnation pressure at the point using this probe, so the positioning of the probe will definitely leads to a disturbance in the flow field, and if it disturbs the flow field, then the measurement which you will take, that may not be the correct one. So, we need to be careful while we are using this probe to measure stagnation pressure. Now, I will try to discuss what are those, the special attention, rather what are those precautions we need to consider while we are placing this probe to measure the stagnation pressure. If we are going to measure stagnation pressure, so there will be the point where I would like to measure the stagnation pressure. So, we will see through a schematic depiction that where that this is a probe, multi-hole probes. So, which hole is used to measure stagnation pressure, and as I said that the positioning of the probe will try to create disturbance in the localized flow field. So, there is a possibility of having heating, this is because sudden stop of the flow velocity. So, that is known as in the zone which is nose of the probe, where stagnation takes place. And the effect of measuring this stagnation pressure will results in a frictional heating, or I can write frictional effects. But this frictional effect can be ignored if it is uniform steady flow, but always we cannot ignore it. So, if this effect cannot be ignored, then the stagnation probe which is placed in parallel to the flow field, flow direction, rather flow field is not the correct word, rather the axis of the probe is parallel to the flow direction. Would not give correct results. So, that means what we understood that in most of the cases, if the flow field is uniform and steady, then if we place the probe whose axis is parallel to the flow direction, then we can ignore the frictional effect, but in most of the cases we cannot ignore the frictional effect. That means the nose where the probe is placed, hole is placed, rather where stagnation takes place, because of the frictional effect the flow field will be disturbed locally and we won't be able to measure the pressure correctly. Now, if that is the case, then what we should consider to get the correct measurement using the probe, we should know. So, when stagnation pressure probe is in the deep in the flow field, I can write that in the a steep stagnation pressure gradient is in steep pressure gradient which is very common. We know, rather you all know that the typical example is inside the boundary layer. So, inside the boundary layer, what will happen? So, if we place a stagnation pressure probe in the region where we have steep pressure gradient, a common example is inside the boundary layer, then what will happen? The positioning of the probe will try to deflect, distort the streamline, and the streamline will try to deflect towards the region of low velocity. So, this if we place this probe knowing fully that in that region velocity pressure steep pressure gradient exists, even we are placing the probe, then the positioning of the probe will try to deflect the streamline and streamlines will be deflect towards the region of low velocity. Eventually, what will happen? If the streamlines are deflected in the region of low velocity, the probe will definitely give the rather will give the measurement of the pressure, but the measurement that is recorded by the probes will not be the correct one, rather it will give the higher measurement of the in the higher side. Then placing of the probe, rather I can say will deflect the streamlines, and the streamlines will be deflected of low velocity, and this effect, the ultimate effect of this phenomenon is that the probe, rather I can write the pressure indicated by the probe, the pressure indicated by the probe is the stagnation pressure, which is higher than the actual value, actual pressure. So, this is the ultimate effect will have that the pressure indicated by the probe will definitely be the stagnation pressure, but the pressure will be the higher than the actual pressure. So, this is one aspect. Now, I said that stagnation pressure probes, the axis of the probes are normally, the probe is placed, which axis of the probe is parallel to the flow direction. Now, question is, if we place the probe which is perpendicular to the direction, to the flow direction, then what will happen? So, when the stagnation pressure probe is placed and perpendicular, or I can write in more generic way that when the stagnation pressure probe axis is placed in such a way that the axis of the probe is not parallel to the flow direction. Then the straightaway answer is the measurement will be erroneous. So, the indicated pressure by the probe is not correct. So, that depends upon the shape of the probes. Now, the degree of wrong results, rather not correct value, that depends upon the shape of the probe. So, not correct, and I am underlining this word correct, and the degree of correctness will depend upon the shape of the probe. See, most important advantage of having, rather of using probe is that we have seen that we can measure pressure using gauges. We have discussed about different gauges starting from conventional one to the low pressure gauges which are used to low pressure measurement, but these pressure probes, as I said, that these probes are used to determine simultaneous measurement of static pressure, total pressure. Most importantly is the flow angle, because in the application of in the turbomachinery, hydraulic machines, we need to measure the flow angles, and in that case the probes are very useful to measure those flow parameters, because we can get all the measurement in the same platform. So, now we will see using, as I said, that we are discussing about multi-hole probes, and multi-hole probes So, we will discuss about the 3-hole probes first, then we will see that using 3-hole probe, rather 3-hole probes are having limitation, and because of that we need to go to discuss, we need to know the working principle of the 4-hole probe, rather to overcome the limitations which are there in 3-hole probe to measure pressure and other flow parameters. The concept or the new design concept of 4-hole probe came, and we will see that if we use 4 hole probe, in fact 5 hole probes are there. If we use 4 hole probes, we can eliminate the problem which is having for 3 hole probe, and how rather by suitably designing the 4 hole probe, rather we can see the 3 hole and 4 hole. So, in 4 hole probes we are having extra hole. So, with the inclusion of additional hole, how we can eliminate the problem that is there with the measurement of pressure using 3 hole probe. Now, but first we will discuss about 3 hole probe, but before that, as I said that multi hole probes are more commonly used to determine several flow parameters. Now, not only that, these multi hole probes are having a few disadvantageous features as compared to other conventional pressure measuring instruments, and those features are: one is simple in operation, low cost, and easy maintenance. So, these three are the important advantageous features these multi hole probes are having, and because of that these probes are used. Now, we will start our discussion using a 3 hole probe, and we will see that if you would like to, we should know the construction of a 3 hole probe, then only we will come to know what is the problem, and if you would like to remove the problem, but we need another kind of probe, then what will be the new design, rather the concept of 4 hole probe. Now, the 3 hole probe, just I will try to show schematically the construction, rather the design of a 3 hole probe, and then we will discuss that what is the limitation of this 3 hole probe is having. This is a wedge shaped 3 hole probe. I am writing a 3 hole wedge probe. Now, this is 1, this is 2, and this angle is alpha, and this is known as yaw angle. Yaw angle alpha, which is greater than 0 as shown from the figure, and So, see, this is the construction of a 3-hole probe. We can see now there are 3 holes, 1, 2 and 3. 1 is the central hole and 2 and 3 are placed, one is left side, other is right side about the axis of the probe. Now alpha, that is yaw angle, because as I said that the probes are used to measure the flow angle. So 2 different angles we can measure, that is yaw angle and the pitch angle. We will see that now the this view is shown in the right side. Now question is, these 3-hole probes basically are not used nowadays, because from the figure itself it is seen that these 3-hole probes, although they are most commonly used probes. So these 3-hole probes, I have drawn only the wedge shape, but there are many other common shapes available now, cylindrical and other things, but these 3-hole probes, which is most common used probe for turbo machine. And in similar research. So this is, nowadays it is not used, but it is, it is most commonly used, but we will see soon that using this probe we cannot measure one important flow parameter, and because of that we need to modify the design of this 3-hole probe, and that is why the concept of 4-hole probe came now, but still it is most commonly used for turbo machines and similar other research. Not only the pressure, rather we also can measure the flow angle. Now see, these 3-hole probes are suited in place where flow is largely 2-dimensional, but we all have studied in fluid mechanics that 2-dimensional flow field, again it is just like an assumption that we can consider that the other direction is infinitely large as compared to the other 2 direction. Now so if you would like to measure flow parameters in places where flow is 3-dimensional, and that is most common scenario, so in those places we cannot use this 3-hole probe. So although it is most commonly used for turbo machines and similar other research, but nowadays it is not used because of this limitation that this probe is used, rather I can say suited in places where flow field, where flow is largely 2-dimensional. So one typical example is that in case of a multi-stage axial turbo machine where hub to tip ratio is large. So as I said that we can take assumption that the one direction is large and ordered large as compared to other 2 dimensions, and flow field we are approximating as if the flow field is 2-dimensional. In those places it is suited, but this is not the common scenario. We will see in most of the cases flow field is 3-dimensional, largely chaotic. In those places this 3-hole probes is not suitable, because one important flow parameter, that is the pitch angle, cannot be, the pitch characteristics of the flow cannot be measured using this probe, because from the schematic we can see the yaw angle can be greater than 0, but with using this probe we cannot have the pitch characteristics, we cannot determine. So this is most suitable, but if we place this probe in a fully 3-dimensional flow field, then what will happen, because we have understood that this is not suitable in, for measuring flow parameters in 3-dimensional flow field, but if we place it by mistake or knowing fully that okay we can measure, then what will happen. So, we have understood that this 3-hole probe are suited for 2-dimensional flow. That means the pitch characteristics of the flow cannot be determined. So, the pitch characteristics of the flow cannot be measured. Using 3-hole probe. So, if we place it for measuring flow quantities, flow parameters in 3-dimensional flow field, then what will happen? That means use of 3-hole probe in 3-dimensional flow field will leads to very appreciable error. In what? Because flow field is 3-dimensional, we would like to measure the flow velocity and pressure we can find, but we would like to measure flow velocities, but the probe is no way responsible to measure, to give any information about the pitch characteristics of the flow. So, if we use this probe either by mistake or by knowingly that okay we can get it. So, eventually the measurement will leads to a very appreciable error in calculating the flow velocity components. In calculating, rather I can write in estimating the velocity components. So, this is what is the most important drawback of using 3-hole probe. So, since central hole is there, another 2 holes are there, one is in the left side, right side. Now, if we connect to, we will see that when we will discuss about the constructional feature of the 4-hole probes, then we will discuss that these pressure probes are drilled radially and they are connected to the lead, those leads, pressure leads. The leads are connected to the manometer. Now, connecting those probe through leads to the manometer, we can measure pressure, but since the pitch angle, the pitch characteristics cannot be measured using 3-hole probe, then if we use it in the 3-dimensional flow field, we will get result, but the results, the measurements, the calculation what we are getting will have appreciable error because the components of velocity components are not the correct one. So, now to circumvent this problem of associated with this probe, the concept of 4-hole probe came into the picture. So, now this 4-hole probe, which is nowadays used mostly largely different shape, conical, cylindrical, wedge shape, but this probe limitation what we have understood that the pitch characteristics which cannot be measured using 3-hole probe can be measured using 4-hole probes. So, the pitch characteristics of flow field can be measured using 4-hole probe. So, that means 3-hole to 4-hole inclusion of an extra hole is responsible only to give us the pitch characteristics, the pitch angle. So, that means addition or inclusion of extra hole or probe will measure the pitch characteristics of flow. So, that means a fourth orifice, a fourth hole which is located at the tip of the probe. So, I can say extra hole, extra orifice. This extra hole or extra orifice which is located at the tip which is hemispherical in shape. So, the extra hole, inclusion of extra hole which is located at the tip and which is having hemispherical shape is responsible to measure the pitch characteristics. So, in 3-hole probe we had one hole which is responsible of measuring the yaw characteristics. Similarly, the inclusion of another hole that is located at the tip is responsible for measuring the pitch characteristics. Now, we will discuss in detail that if you would like to include one extra, rather when you are including extra hole orifice in the configuration of a probe, then and that too which is placed at the tip of the probe and which is having hemispherical shape, and by placing that extra probe, how we can measure the pitch characteristics, that is the pitch angle of the flow. Flow angle is very important, and from there by measuring the so we will measure static pressure, we will measure stagnation pressure, and also we will measure the yaw angle, pitch angle. So, these 4 parameters we will measure using 4-hole probes, and the constructional feature of the 4-hole probe together with its operational principle, and from the measured value of pressure how we can calculate the velocity components, that part we will discuss in detail in my next class. So, with this I stop my discussion today and we will continue in the next class. Thank you.